Hi and welcome to the Stock Talk, a dynamic shortest path toolbox, low congestion Vertex Sparsifiers and their applications. My name is Simon Meyerhans and this is joint work with Rasmus King and Maximilian Probst-Gutenberg. We are all based at ETH Zurich. The main problem that we solve is the so-called APSP problem. APSP is short for all pairs shortest paths, and it's a problem on a fully dynamic graph. So you imagine a graph like the one depicted below that receives updates that delete edges and add edges. And you want to have a data structure that maintains query access to approximate pairwise distances in this fully dynamic, as we call it, graph. Our main result is then that for a fully dynamic graph G with polynomially bounded integral edge lengths, our algorithm processes updates add edge and delete edge in worst case time e to the little o of 1 or subpolynomial per update. And furthermore, it answers distance queries, approximate distance u to v, such that the returned distance approximations are only off by a subpolynomial factor. It answers such distance queries in time order log of the number of edges. Furthermore, our data structure gives implicit path access. This means that a forest F is explicitly maintained in memory, and this forest F has a flat embedding into G. With a flat embedding, we just mean that every edge in the forest directly maps to a single edge in the graph G. Furthermore, after every distance query, like let's say from V1 to V4 in this case, the algorithm returns pointers to two vertices in this flat embedding forest F, such that the unique forest path between these two vertices, when mapped back to G, witnesses the approximate distance returned by the algorithm. So you see that if I map this path from the forest here on the right to this graph G on the left, I get this dotted line path, which is an approximate shortest path, but it's not a simple path as you see. It may loop. The implicit access theorem then informally states that our data structure explicitly maintains a dynamic forest F, such that every graph edge only appears subpolynomial times in F, or phrased differently, if we map the forest edges back to the graph, the congestion is at most a subpolynomial factor. Furthermore, for every distance query approximate distance, the data structure returns two vertices in the forest, such that the forest path is approximately or is an approximately shortest path, or said in different terms, witnesses the approximation that our data structure returns. This turns out to be crucial for example, maintaining flows via link-cut trees and allows us to get our decremental SSSP algorithm deterministically, and is also used heavily for our incremental flow results. You can just imagine that you can, even if the distance witnessing path is very long, ask interesting queries about this path with, for example, a link-cut tree or other tree data structures that can run on this explicitly maintained dynamic forest F and get things about this path without having to enumerate the path. If we compare with previous work, we see that their APSP problem has received significant attention in the last years. The first set of papers by Hensinger, Kroeninger, Nanokai, Cheshik, Foster, Goranci, and Hensinger all work in the so-called decremental setting against an oblivious adversary. This means that the graph only receives edge deletions and that the algorithm is randomized and the adversary crucially can't know the answers of the data structures before making up their mind for the next query. The algorithm is further amortized and the update time is subpolynomial. Then the algorithms by Chutsoy, Bernstein, Saranurak, Probst-Gutenberg both get, again, decremental updates, but now against an adaptive adversary, which means that the adversary can know the previous answers of the data structure before making up their mind for the next query. This is absolutely crucial if you want to use this data structure in a black box manner for an algorithm, because usually the queries that an algorithm does depend on the previous answers of the data structure, and therefore the oblivious adversary assumption is easily broken in this setting. Forster, Nassari, and Probst-Gutenberg further got an algorithm that deals with incremental updates, which are just edge insertions, again against an adaptive adversary, and the update time is just polylogarithmic. The algorithm is amortized, but we believe that one could de-amortize it at the cost of going to a subpolynomial update time / approximation. Then the algorithms by Chutsoy, Tsang, and Foster, Goranzi, Nazzari, and Scarlatos finally got fully dynamic updates. Again against an adaptive adversary, but they crucially required amortization, which just means that they don't answer all queries fast, but just the average query fast. Then our algorithm is the first one to process fully dynamic updates without the need of amortization, and the update and query time is again subpolynomial. Furthermore, of all the algorithms here, our algorithm is the only one that gives implicit path access, which just means that we have this forest that I talked about in the previous slide. There's a parallel work that I want to mention by Heupler, Long, and Saranurak that also manages to get rid of the amortization. And furthermore, they can get better approximation for verse update time, since they are able to trade off the update time and the amortization in a smooth manner. However, they do not give implicit path access, which is crucial to many applications. For the remainder of this talk, I want to jump into the details of our APSP algorithm, since even though we give strong guarantees, I think it's also instructive to see the inner workings because they are quite different from previous approaches and arguably simpler. The main ingredients are distance-based and can be broken down into the Andoni-Stein-Zong vertex sparsifier and core graphs. Core graphs have been driving a lot of the recent progress on flow algorithms. What is the Andoni-Stein-Zong vertex sparsifier? I'm going to give a slightly adapted version here in this talk, but the idea is that one selects a set of terminals, I will call them A, which is a subset of the vertex set V, such that for every vertex, the ball around it that includes everybody that's closer than the closest terminal has at most k vertices in it. We will choose k later, but you should think of k as like some large subpolynomial factor, which will roughly be the size reduction if we go from V to A as well. The idea is then to consider the following path collection P. For every vertex V, we add the shortest path between U and V and W, where U and W are two vertices inside this ball that contains all the vertices until you hit somebody in A. And we will also add the pairwise distances where one of the two vertices is just outside, like I drew here. So if W is just in the neighborhood of somebody that's inside the ball, that's also fine. Here at the bottom, I drew such a path from one vertex U to a vertex W that's in the neighborhood of the ball. So it's just outside. If we assume that the degree of every vertex is at most k, which we will have to do, then the path collection is still actually quite small. There are at most k cubed times the number of vertices paths in this path collection. So if we think of k as a subpolynomial factor, then this is still an almost linear amount of paths. To get use out of these paths, we have to define pivots and their projections to paths between pivots. The pivot of a vertex V is just the closest vertex in the terminal set A, and the projection of the path is just taking a path in the vertex in the path set P and take both endpoints and add the shortest path to the respective pivot of the two. This is again illustrated with this picture down below, where we have this dashed line that corresponds to the path, and then the two dotted lines, which correspond to the shortest paths to the respective pivots, and then this whole path would be in P prime. Why does this yield good distance approximation between pivots or between the terminals? Well, consider the shortest path between any pair of terminals in the real graph from here to here. Then the links that go from pivot to pivot in this setup are always contained in the path set P prime. Why is that? Well, we can just follow the shortest path until we have the first vertex that has a different pivot. And then the path to this vertex has to be inside the path collection P. Therefore, the projection is in P prime, which just means that we can do these jumps between red vertices as indicated in this picture. Furthermore, we can observe that if we measure the distance A and the distance B in this picture, the distance B is always smaller than the distance A, which directly gives you the constant approximation that you want because the detour is at most then like 2A or something. Our main idea is that one can quite easily dynamize these AS set paths. How do you do that? Well, whenever a vertex is touched, which we will just take to mean that it's incident to an insertion or a deletion, we add it to the terminal set A. Then it's quite easy to observe that every vertex has at most k possible pivots. And these are the vertices that are in this ball from the start. Why is that? Well, whenever you try to mess with the distance structure inside this ball in any way, you add the closest vertex as a pivot anyway, so the ball just shrinks. But this means that even the shortest paths to the pivots are preserved. And this then in turn makes us want to anticipate all k possible pivots and add the shortest paths to these pivots as extra paths from the start. This only adds some polynomial in k extra paths, and it's easy to show that this then contains all the paths that will be relevant throughout. So if we have a dynamic data structure that makes sure that these paths in this initial path collection are preserved, then we know that we will be good throughout. The very rough idea is then to compute a low stretch tree that will roughly preserve half the paths and repeat until all paths are preserved. Since this doesn't work so well dynamically, we resort to core graphs, which are a variant of low stretch trees where instead of a tree, you get a forest, but the approximation is better between edges that don't cross the forest. It's a very, very loose way of saying it. We will add a core or a forest component for each touched vertex / pivot, and this will reduce the vertex count. And then, I won't go into this, we finally have to reduce the edge count as well, which we do by a dynamic spanner. Then we just recurse, which yields our vertex sparsifier. So let's talk a little bit more about core graphs. Core graphs contain these vertices that are in A labeled in red, as well as forest components, which I will call cores. And they measure the stretch of all edges that are not part of the core graph, which just means that they're not in one of the trees in the forest. The stretch of a so-called internal edge is measured as in a usual low stretch tree via the length of the detour divided by the length of the edge. Whereas the stretch of a cross edge, which is just an edge that goes across two forest components, is measured as the length of the path to the root of the core on the left and the path to the root of the core on the right, plus the length of the edge divided by the length of the edge. So internal edges will disappear once the cores are contracted, whereas cross edges will be mapped to be edges between two roots of the cores. Core graphs give you that the maximum stretch for size reduction approximately k as we had previously is k, and the average stretch is just polylog. Furthermore, you can quite easily dynamically maintain core graphs such that the stretch of edges only decreases over time. This means that if we are good with respect to the original path collection, we will stay good throughout, at least until we have to rebuild. Finally, layering this construction yields a vertex sparsifier. Distances can be queried rather directly because this vertex sparsifier contains the Torup-Zwick distance oracles, and an explicit forest representing the paths can be extracted by gluing together these core graph components in a more or less direct way. Thanks a lot for listening.